Good morning, ladies and gentlemen. My name is Ayesha Majeed, and I will be presenting the paper Modeling Fog Offloading Performance, co-authored with my PhD supervisors. The outline of today's presentation will be on the background behind this research. I will discuss container-based offloading approaches, followed by the model to estimate downtime, followed by the key results, and then looking forward to work in this area. To address the issue of high latency, fog computing is emerging to overcome this issue by bringing the cloud closer to IoT devices. This figure depicts the scenarios of offloading. It can be from the cloud to fog, which refers to transferring services of an application from a cloud resource onto a fog resource to meet latency and ingress bandwidth demands. Or it can be from fog to cloud. This refers to transferring services that are resident on a fog resource to the cloud. This may be done due to a change in the life cycle of the application, that is, the service on the fog resource needs to be terminated and resumed on the cloud from where it was originally offloaded. Or it can be from device to fog offloading. Basically, this refers to transferring services of an application from one or a collection of end-user devices to a fog resource. This is done in order to augment the limited resources of end-user devices. Although fog offloading is reported to be beneficial, applications can adversely affected if there are large offloading overheads. The large offloading overhead results in application downtime affecting user experience. The time taken to offload a service is an indicator of the downtime of an application. The estimation-based method to predict downtime can be useful in the following cases. In automated fog software development environments, to provide application developers estimates of deployment time and downtime of services as they design and develop their fog applications. Second benefit will be for adaptive decision making in fog orchestration platforms, where it may be possible to offload multiple combination of services in a transient environment using different migration techniques. Predictive models can make decisions on which offloading technique is best suited given the current state of the system and the associated requirements. Third benefit would be that predictive models can provide near accurate estimates of the time taken to offload a service, and it can be useful for in simulation platforms that are used by researchers or practitioners that don't have access to the physical infrastructure. There are different approaches supported by Docker container technology to offload container from the cloud to the fog or vice versa. Docker supports two migration techniques. Stateful, the state of running application is transferred within the container image. Stateful migration is achieved using check and restore in user space. The second approach is stateless, in which the state of the application is not transferred. Instead, a separate instance of the container is run somewhere else without its previous state. Stateless migration techniques include methods such as save and load, pull and push, export and import. This research investigates into two different migration techniques that can be used for offloading, and therefore two migration stateless and stateful migration technique is considered within the scope of this paper. Figure shows the cloud to fog offloading scenario is using the save and load migration technique. Other techniques are mentioned in the paper. Docker packages an application in the form of images that consist of a file system with the required libraries. The goal of this technique is to transfer the image of a running and the underlying base layers. This offloading technique is a 5-step method. Step 1, commit. A container is instantiated when it boots up from a series of base image layers when there is a request for offloading from the cloud server. The commit operation stops the running container and saves the current state of the container, referred to as committed image. Step number 2, save. The save operation converts the committed image to a compressed file. Step number 3, the compressed image file is transferred to fog resource using a network transfer protocol. Step number 4, load. This operation decompresses the tar image file and loads it from the hard disk to local registry of fog resource. Step 5, a container from the image in the registry is booted up on the Fog resource. Downtime is the time taken for all the 5 steps mentioned. For estimating downtime, 25 metrics, including runtime metrics such as CPU utilization and memory utilization, and offline metrics such as network bandwidth and container image size. We have identified 2 methods to estimate the downtime. The first method is using a collective method, which is a reference to the use of a single model that estimates the downtime. The collective method uses all the 25 metrics as an input to predict the downtime. The second method is using an individual method, which refers to the use of separate models for estimating downtime. The performance of model is assessed using R-square, mean absolute error, and mean absolute percentage error. With respect to R-square, it is observed that 72 to 99% of the chosen input parameters, they influence the downtime. And with respect to mean absolute error, as low as 4.2% is obtained. Estimation-based model provides estimates of downtime of services on the fog. Service downtime cannot be afforded by latency-critical applications that have real-time constraints such as self-driving cars and industrial robots. These latency-critical applications are underpinned by deep neural networks. So deep neural networks can be distributed across the cloud and the fog to improve efficiency of latency-critical applications. At runtime, the configuration of distribution needs to be changed when the application conditions such as network speed change. So to reduce the service downtime when the operation conditions change, we developed a framework that reduces service downtime when reconfiguring the DNS across the cloud and the edge. Thank you for your kind attention to my presentation. If you have any queries, I would be happy to have your comments via email. That will help me shape my research better. Thank you.